Hello everyone, welcome to my video on sets of real numbers. The first set that we deal with is the natural numbers, which we denote as boldface n. Okay, and the natural numbers is the set of positive whole numbers. So as you can see here is this set over here, which we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth. So think of the natural numbers as a set as numbers which you count with. So 1, 2, 3, 4, 5. Notice that it does not include 0. Because when you count, you don't start with 0, 1, 2, 3, 4. You start with 1, 2, 3, 4, 5, 6, 7. So it's all the positive whole numbers. Okay, so that's the first set. That's the set of natural numbers. The next set that we have is the integers, which we denote as boldface z, which is the set of positive and negative whole numbers. So it's the exact same thing as the naturals, but now we include also the negative whole numbers. So -3, -2, -1. In this set here, we do include 0. Okay, and then 1, 2, 3, 4, 5, 6, 7, so on and so forth. So we go down all the way to negative infinity and positive infinity. Okay, so here there are no decimals. So next we have the set of rational numbers, which we denote as boldface q. And formally we could write it as the set of p divided by q. That's what's written here, such that p and q belong to z. So this is saying that p and q are integers. They could be positive or negative, it doesn't matter. But q also cannot be 0, so you cannot divide by 0. That's what it's saying. This is the formal definition, but more informally, think of it as the set of fractions, terminating decimals, or infinitely repeating decimals. Okay, so let's take a look at some examples to see what we mean. So the set of rational numbers includes fractions, terminating decimals, infinitely repeating decimals. If we look at our examples here, we have 1 over 9, -3 over 4, and 3. Remember that for the third example here, 3, every number is over 1. So you can think of 3 as 3 over 1. So it's actually a fraction. So these are examples of rational numbers where these guys are all fractions. Okay, so the second you see a fraction and the numbers are integers, 1 and 9 are integers, 3 and 4 are integers, 3 and 1 are integers, and when they're dividing, we have fractions. So this is a rational number. The next two examples that we have is 0.5 and 2.875. These are examples of terminating decimals. That means that we have a decimal and it stops. So 0.5, it stops at 5. That right away is a rational number. Here it's 2.875. It took a bit more numbers, but at the end it stops here at 5 again. So these are terminating decimals, so they stop. Therefore, they're rational numbers. And the last set that we have are the infinitely repeating decimals. This is in numbers such as 0.33 repeating, so 0.333333 forever. So the second you see this bar on top, it means that those numbers repeat. So 0.33 repeats. If it would have been just 0.33 with no bar on top, that's a terminating decimal that stops. But in this case here, you have a bar on top. This means that the 3's repeat. We just don't write it. So think of 0.33 with the bar on top as 0.333333, and it continues forever. Okay. When this happens, we have a infinitely repeating decimal. And these are rational numbers. Okay, so make sure there's a pattern that repeats. In this case, the second example here, it's 0.123, 123, 123, 123 forever. It continues with that pattern. Therefore, that's a rational number. Okay, let's look at our next set. So the next set that we have here are the irrational numbers. So this is the exact opposite of the rational numbers. So we're dealing with irrational now. And the notation that we use is boldface q, either complement, the little c on top. I've also seen this notation here, so some teachers put a bar on top and some teachers put a prime. Q prime or Q bar or Q to the C. Whichever notation you use, it's fine. Some teachers I've seen also use the letter I. I wouldn't use that. I've never seen a book that uses I for irrational numbers, but this is the typical notation that we use. And the irrational numbers are the set of non-terminating, so they don't stop, and non-repeating. There's no non-repeating decimals. There's no pattern that emerges. Okay, so think of it as pi. pi never ends, and the numbers that show up in pi are always different. So if you type in pi in your calculator, it's 3.141592654. So all those numbers are different, and this number, if you plug it into a computer that has more precision than a calculator, you will see that the numbers never repeat. So that's an example of an irrational number. Another example that you have is a square root of 2, or a square root of a prime number. So square root of 2 as well, if you plug it into your calculator, square root of 2, you get 1.414, and then it switches 213562. So all these numbers are different. There's no pattern that emerges, so therefore this is non-terminating, so it never stops, and non-repeating. There's no pattern. So all the numbers are different. The next example here, be careful, this is kind of a trick, pi over 4. So you might be thinking, wait, there's a fraction. Isn't this rational, not irrational? Well, be careful, because the definition of a rational number, it has both the numbers, the numerator and the denominator, have to be integers, whole numbers. 4 is a whole number, it's an integer, but pi is not. It's not a whole number. If it was 3 over 4, that's fine. But since we have pi over 4, this ends up being an irrational number, not rational. Okay. Next we have the square root of negative square root of 13. Once again, this is irrational. And lastly, we have e. E, if you plug it into your calculator, Euler's constant, it's 2.718281828. So it looks like there's a pattern that emerges, but if you plug it into a computer application software, you're going to see that it actually, there's no pattern that emerges. It's irrational. Okay, so this is like 2.718, and the numbers keep changing. Okay, so it doesn't stop, and there's no repeating sequence of numbers. Okay, so that's the set of irrational numbers. And then if we combine all the sets that we saw today, this is the real numbers. Real numbers, which we denote as boldface R. Okay, so this is the set of all numbers. Think of your number line. And we call it real numbers because we actually have in math imaginary numbers, which we won't see, we'll see later on, we won't see in this course. We're going to stick to just the real numbers. So that includes the natural numbers, the integers, rational, and irrationals. All that together combined, that makes up for the real number line. Okay, let's take a look at some examples. Okay, so in this example here, we're asked to classify the following list of numbers. So we're given pi over 3, 10, negative 4 over 7, negative square root of 9, 10.1234 repeating, square root of 169, square root of 36 divided by square root of 9, 14.8, and square root of 4 divided by 35. Okay, and our job is to classify which ones are naturals, which ones are integers, which ones are rational, and which ones are irrational numbers. Okay, so the best advice I could give you is to always simplify before you start classifying your numbers. Okay, so here pi over 3 is fine, 10 is fine, negative 4 over 7, that's fine as well. But maybe this one over here, negative square root of 9. What's the square root of 9? Use your calculator and simplify. Really, this is the same thing as just saying negative 3. So instead of thinking of it as negative square root of 9, this is really just negative 3, and then it's easier to classify it. The next one, 10.1234, we see a repeating. There's a bar on top. So you should have an idea where to classify that. Square root of 169. Let's use our calculator. Can we simplify this? Square root of 169. On the calculator, this gives us really just 13. So it looks like it's irrational because we have a square root, but be careful, always simplify first. In this case, it's not. Even over here, we have square root of 36 divided by square root of 9. What's the square root of 36? That's really just 6. And the square root of 9, we saw it above here, is really just 3. So really, this is just the fraction 6 over 3. But we could reduce that even further. What's 6 divided by 3? That's really just 2. So this was a fancy way of just writing the number 2. Okay, and now this is easier to classify. 14.8, that's fine, there's nothing to do. And then lastly, we have the square root of 4 over 35. So let's do 4 divided by 35. And then take the square root of it. You get 0.338061701, and this is a non-terminating, non-repeating pattern. So there's nothing to do here. Now we're ready to classify. So the first one we have is pi over 3. Since you see pi, although we have a fraction as we saw in the previous example, this is still irrational. So let's put that one in here. Let me put it in red. Pi over 3 comes here. This is the answers. So that one's done. Pi over 3 is irrational because we have pi in it. And again, even though you see a fraction, be careful. It's not rational because for it to be rational, the numerator and the denominator have to be whole numbers. Since pi on the top is not a whole number, it's irrational. So you could also check this on your calculator. Pi divided by 3. You get 1.0471975551, and all those numbers are different. And it's non-terminating, so irrational. Next we have 10. This is easy to classify. 10 is positive and it's a whole number, so it's natural. Negative 4 over 7, we have a fraction. That's rational. That's done. Negative square root of 9 was just really negative 3. So if you're thinking it's natural, be careful. Natural is only positive numbers, positive whole numbers. Since it's negative, that falls under the integers. So instead of writing negative 3, I'm going to write negative square root of 9. So a couple of tricks here, just be careful, always simplify. 10.1234, repeating. Since there's the repeating bar, right away I know that's rational. It's a repeating decimal. This is done, this is done. Square root of 169, we got is really just 13. That's a natural number. Square root of 169. That's done. Square root of 36 over square root of 9 was really just 2. Again, that's a natural number. It doesn't look like it, but it's actually not natural. Once you simplify, that's done. 14.8, it's a terminating decimal. That's irrational. Done. And lastly, 4 over 35. Then you take the square root. That's irrational. Okay. And this is our solution. Okay. So great work. Let's take a look at another example. Okay, so in this example here, they're asked to consider the following list of numbers. So we have pi over 2, negative square root of 225, 9 over 14, 3.6 repeating, square root of 14, negative pi over pi, and square root of 2, all that squared. And they ask how many of these numbers are irrational. This is a very typical multiple choice question that they ask on exams. So let's go ahead and do this together. Again, I urge you guys to pause the video, try it on your own, see if you get the same answer as me. So let's go ahead and start. The first number we have is pi over 2. We've seen this example. It looks like a fraction. They're trying to trick us, but don't fall for it because it's not rational. Because in order to have a rational, again, the numerator and the denominator have to be whole numbers. In this case, pi is on top. That's not a whole number. It's a decimal. So this one here is irrational. So let me put a little 1 over here. That's our first one. Next one, we have the square root of 225. That looks like it's rational because we have a square root in it, but make sure to simplify. Check on your calculator. Square root of 225 is really just 15. So this is just negative 15. Is that irrational? No. So that one doesn't count. 9 over 14, that's a fraction. Right away we know it's rational, so we don't count that one. We're looking for irrational. 3.6 repeating, is that irrational? No, because we have a repeating decimal. That's rational. Square root of 14, let's check. Square root of 14, it's non-repeating. 3.7416577387. So this is a non-terminating, non-repeating. Therefore it's rational. This is our second. It's irrational. This is our second. Next one, we have negative pi over pi. So you see pi right away, you're thinking it's rational. This is a bit of a trick. Negative pi, anything divided by itself is 1. So pi over pi, they cancel each other out. So we actually just get negative 1. So it's really not irrational. It's actually just an integer. So this is a bit of a trick because you see pi right away, you're thinking it's irrational, but that's not always the case. They could try to trick us. Don't fall for these tricks. so we don't count this one here. And last one, we have square root of 2 squared. We saw in the last example that square root of 2 is irrational. But in this case here, if you do square root of 2 times square root of 2, because that's what squared means, you multiply it by itself, do this on your calculator, and this is really just 2. So this is just a natural number. So it's not irrational. Therefore, only 2 of these options are irrational. The answer is B. Okay. So be careful for these little tricks. Keep up the great work, and I'll see you in the next video.